Hello everyone, welcome to the today's knowledge session. Today I would like to discuss about metaprogramming. That's one of the popular, programming paradigm, and that's in place from quite some time, like 1970s and 80s, and it was used with a lot of old languages or popular languages like Lisp for some of the artificial intelligence based use cases. So today we will briefly try to discuss what exactly is the metaprogramming, like what are some of its trade-offs, what are some of its applications, who are its intended audiences, and how I can use it in the functional programming, like with Scala or with any other functional programming. How can I use it? So let's follow all the knowledge etiquettes and manners because the lack of them is a huge turnoff. So let's join the session on time, and let's all of us be in the silent mode. If there are any kind of queries, so let me know, and let's try to avoid any kind of disturbance in the between during the session. And if there is any kind of feedback for me end of the session, please do let me know. So the agenda for today's session mostly would be like we will be discussing the metaprogramming in brief, like how it is being used in different programming world, even in for interpreted languages, for compiled languages. So we will be discussing all those things. We will discuss some of its trade-offs. Then we will try to briefly touch base upon how I can use it in the functional programming, or how I can use in a functional style along with Scala 3. That's what would be the intent of the session would be. So since metaprogramming mostly is used with the compiled languages and along with the interpreted languages also it can be used. So let's first try to see its magic, what kind of benefits it provides me at compile times. So it's a programming technique in which your program has the ability to treat other program as a data. So when I say data, you can understand the data as a metadata. So what that means is that your program can be designed to read, to generate, analyze, or transform any other program, and even it can modify itself while running. So that kind of technique metaprogramming is. If you have heard of all the compilers, transpilers, or assemblers, so these are some of the examples of metaprograms, the data that I was talking that your source code has. So they take a program in one form and they can apply some kind of update or transformations, and then they can transform them into a machine code, bytecode, or even a source code based upon what type of language it is, whether it's a compiled or it's an interpreted language. So one of the popular techniques, and it's like was used like from quite long with Lisp for some of the artificial based applications there it was used. And when a programming language is its own meta language, so that basically thing is called as reflection. So reflection is one of the I can say key features or one of the important features for any programming language in to facilitate any meta programming technique. So let's focus on this properly. Also, what happens, metaprogramming can move all your computations from runtime to compile time. Thereby it enables us that self-modifying code, it enables those things. Hence a program is designed in such a way that it can read, analyze, and transform other programs while it is running. So this self-modifying capability of the code, this is something you can understand what metaprogramming is. And this style of programming basically falls under a generic programming, where programming language itself is a first class data type. Now you might have a question, what are some of the benefits or pros when a language becomes its own data type? So this is very useful because it allows one to write code without the concern of specifying the data type, since they can be supplied as parameters whenever you want like to use. So let's try to understand this with the help of a block diagram. So let's take a simple example. You have any compiled language like Scala, Rust, Go that compiles your source code into the binary code, means the object code which your machine can understand. Then it basically loads a program instruction which machine can execute. Now, if you invoke any kind of metaprogramming technique, metaprogramming means meta program, so it can further update or transform your program instruction instruction and it can make it, do some extra work. So, but for that you need some kind of structure. So we will see what are the different representations in which I can create a meta program in subsequent sections. But as of now, you can understand something like, once your basically program gets executed, further you can invoke a meta program, and using this meta program you can make your code do certain extra things. So means you are basically updating the functionality. So that basically thing is basically meta programming in case of a compiled language. Now, similarly, for any interpreted language, when your source code, since in the interpreted language, basically the high-level instruction itself can be executed by the machine, that's understood a machine. So basically, what happens in actual thing, since it basically can pass your code into the abstract syntax tree, and then your basically interpreter basically evaluates that code, and now from this interpreted code, you have to extract the meta program, and then further this meta program will be evaluated by the meta program interpreter, and then it can be either invoked in this primary interpreter only, or the other thing could be using this meta program like you were doing in case of a what you say compiled language. You can simply update your abstract syntax tree AST, and then you can further run the program with some extra transformations. That's how it works. So metaprogramming usually works, I can say, in one of the three ways. Like the first approach could be we expose the internals of a runtime engine to the programming code through some kind of APS. That could be one way. Second way could be, some kind of dynamic. Sorry. The second approach could be the dynamic execution of your expressions that can contain some kind of programming commands that often is composed from some kind of string. So they can also be from some other methods using that can be passed either as some arguments or context. Simple example could be in case of a JavaScript. So when a program can write program, that's the second way of using a meta programming. And the third way is like when you have some kind of program based transformation, that is when you're creating some kind of compiler or assembler. So when you have to step outside the language itself, that's the third way you can use meta programming technique. So which basically in case of program transformations also, it accepts the language descriptions and carry out some kind of transformation that you have given as an input on that particular language, and this allows meta programming to be applied virtually to any kind of language, whether it's a compiled or it's an interpreted language, without any regard to like whether that target language has inbuilt meta programming abilities of its own or not. Now let's try to understand what are the different ways I can create a meta program that we have talked previously in the block diagram, or what are the different ways I can represent my program as a data. So string is one of the common ways through which I can present my program in a form of data. Another is the abstract syntax tree, which I'm assuming most of us would be familiar. In case not, so let's understand with a simple example. You have a simple, expression like 2 plus 3. You have to perform some kind of binary operation. So basically, an AST for this particular thing will be abstract syntax tree, then followed by whatever is the binary operation that you want to perform. Then again, the abstract syntax tree, what is the type of operands that I am giving. So 2 is one type, another is basically 3, that both are of n type. So this is the abstract syntax representation for this particular expression. Now on this abstract syntax tree only, two more basically ways or approaches are built. One is called as up ML, that is up meta level, and the second is down meta level. So this up ML also represents an AST only, but it is quoted by chunks of a normal program syntax. So what happens? For example, again you have the same expression 2 plus 3. So when you say you have to create a up meta level for this, it will be something of this form, this representation. Whereas down ML is one more step ahead of it. What you're trying to do, if there is any kind of what you say, you have to express some kind of holes or other kind of transformations you want to do in up ML, so you can do using this down ML. So this inside this holes you can perform any kind of arbitrary computation, means you can do some kind of evaluation of your up ML, and that computation ultimately should again yield an AST. So you can understand these two as a wrapper on the existing AST, and that's other ways to represent your program or your any kind of expression or any kind of your source code in the form of a meta program or in a form of data. So let's take a simple example of down meta level. So I'm using the same expression 2 plus 3. I am saying that I can represent this expression something like a function of f, which is basically into 4. So when I further break down this thing, so you can understand, let's say I'm given an expression m, which is basically of this type. So let's say I'm assuming the value of x as 4. So if you put in this thing, so you can further break it down again into the same expression, that is 2 plus 3, that is the original AST. So up meta levels and down meta levels are nothing, but it's representing a AST only, but you're doing some kind of internal computation or some kind of transformation in between. That's what it is doing. And the representations are using this up arrow key and the down arrow key. That's how it is used. So these are some of the common ways that I use across different languages to represent any program in a meta program or in the form of a data. Now let's try to understand, like what are some of the application that will give you more what you say broader idea where I can use this meta programming techniques, or why should I learn meta programming. So compilers and interpreters, like we discussed in the start of the session, is again implemented through this meta programming. If you have heard about the ORMs or any kind of GUIs code generation that we get in our IDs, Eclipse, NetBeans or IntelliJ, so all these code generation can be done with the help of a meta programming technique. If you heard of domain specific language, which basically helps business to interact with your developers and everyone, so those kind of what you say terminologies when we use in our code base, so domain specific languages, that so that languages can be built using a meta programming technique. We might have used a lot of profiling tools like JMeter, Visual VM, and those kind of things. So a lot of profiling tools and test coverage tools can be built using one of the meta programming techniques. Now at the same time, it's also very important to understand, like I am doing some extra effort, I'm converting my program to this meta program, I'm creating some data out of it. Do I get some kind of benefits really, or it's a overhead or a added effort? So let's try to understand what are some of the benefits that this meta programming technique can provide you in a programming language or in the programming world. So code extensibility, that is something that's a generic programming what you say requirement, or in any application it's a requirement. So with meta programming, code can be treated as data, and hence it's allows us to extend the programs and reuse them. So extensibility is one of the main benefits that it provides. If I talk about the performance, so since it is useful in pushing all the computations from runtime to compile time, so I can again enhance the performance of my code. At the same time, meta programs can help us to tune the programs to specific architectures. Plus it also enables a lot of abstraction without any kind of runtime penalties. So these kind of some performance benefits that it provides. Again, like functional programming languages are like known because they're less verbose compared to object oriented paradigm. So again, meta programming technique also provides you of that benefit of it's less verbose, less code you have to write, less maintainability will be there, less bugs will be there, because metaprogramming automates that writing of code, reduces all your manual effort. So a simple example if I would have to take would be the use of macros. So they save the development time and promotes a reusable code. So this way I can remove all my boilerplate code using any by following some of the metaprogramming techniques that programming language provides me. So another benefit I can think of is like accuracy, if I have to talk about. So compiling the code from any high level language like Scala or any other high level language to machine code or a byte code, this is automated. It's not a manual effort or manual process in meta programming. So again, this enhances my program basically ability as well as accuracy, and reduces the number of bugs that would be there in code. One more important feature of metaprogramming is reasoning. That's basically because when you create a metaprogram, for example, if you have to think in terms of type checkers, if you have used, or if you have used any kind of flow analyzer, if you have used, so they can help to discover or figure out or filter out a lot of properties about your programs. For example, I have some ancestral code or some code which is like there from long time, and now I have to come and work on it. If I have a metaprogram of it, so I would be able to figure out what all are the key characteristics or properties of this program, and that way I can validate the behavior, and it will help me to read the code to understand that any existing code which was not written by me but by some other developer. So this way reasoning thing is another feature that basically metaprogramming gives us as a benefit. Now, if I have to also think in terms of limitations, so debugging is definitely the first limitation or the issue that I can think of, because with meta programs, like the tools that as of now it provides, they're not that much mature. So debugging sometimes becomes really very hard. It's like not like kind of inbuilt things that comes with a lot of IDs and all, or with the meta program tools that it comes. Data representation. So we have seen string was one of the ways through which I can create meta programs, or through which I can represent my source code in a form of a data. So string we know is can lead to kind of insecure code, especially when they're coming from some kind of untrusted sources. So writing code as a string can also reduce my overall code readability, and it can introduce a lot of new bugs, especially if it's coming from some source which I can't trust on. So data representation using string is one of the another what is a limit of meta programming. Then learning curve, definitely it's really a steep curve. It's really hard for beginners, somebody who might not be very familiar with the constructs of what you say languages like Lisp, or haven't seen how macros are used in Lisp, might find it little difficult in the beginning to learn. So that's again what it's is a limitation for it. The learning curve is steep. Now let's see some of the real-time use cases where I'm actually using the meta programming. So with this, you guys would be able to relate also. So play framework, most of us must have used. So that's using metaprogramming. Or if we talk about the CATs, the advanced function library that's built on top of Scalas, which is trying to overcome some of the limits of Scala. So CATs is again using a lot of metaprogramming techniques. Sleek, if I talk, or Spray or Staples I talk about, they all have some inbuilt capabilities for metaprogramming, and they basically try to solve a lot of issues with respect to macros and a lot of other things with respect to reflections and all, that can be easily achievable with the for using these frameworks or these libraries and tool sets. Now let's try to understand how I can use this meta programming thing in my Scala. So that is what we let's check it out. So that will give us a brief idea where exactly are the updated features. So I will try to talk or cover in terms of Scala 3. So Scala 3 is having some of the fundamental facilities with respect to meta programming that has come. So inline is the first basically feature. So inline is like added as a modifier in Scala 3 that basically ensures that the definition will be inlined at the point where it is used. So the what was the primary intent or motivation behind this inline? It was just to reduce the overhead that the behind the function calls, and whenever you're trying to access some kind of values. So inline was introduced as a modifier, and the expansion was performed by Scala compiler using the typer compiler phase. So that's how it was using. The next fundamental feature that has come in Scala 3 is compile time operations. They are like, you can understand them like as some kind of helper functions or definitions that are introduced as some in the standard libraries that provides me some support for compile time operation over values as well as on the types. So those kind of basically some standardizations has been done to some existing libraries, which can be achieved with the help of these compile time operations. Then macros, you all must be aware in some or the other format, that where you can replace a particular expression and you can keep on reusing it. When you have to make a change, you can simply replace, make a change over there, and you don't have to make a change over at the 10 places. So macros in Scala 3 is like using two fundamental operations that we will be discussing and seeing in details. Quotation and splicing it is using, that tries to convert again your source code into some meta program. Basically it gives it like a tree like representation, AST it gives it, and you can actually start representing your source code in the form of some quoted expressions you can express. So we will see those examples. Then reflection is another what do you say fundamental feature that Scala 3 has added. So again, quotations like were like, I can say some kind of black box representation of code that were there. So they can be further parameterized and composed using splices, if you have heard. So reflections can be now used in that way. And now they've also added tasty reflection, that is the typed abstract syntax trees. That's a kind of serialized in some of binary formats. So this tasty reflection gives another way to analyze the code structure by actually partly revealing the presentation and the type of a piece of code, whatever you're using in your standard API. So reflection along with tasty inspection is getting used over here. And yeah, the runtimes changing, that was another benefit. So just if you have to make your code generation depend on runtime, and so that can be achieved by adding a dependency with respect to this. And this way macros can construct codes at compile time, and staging lets the program construct new code at runtime. That's what basically is the differences. And that way your code generation can depend not only on static data but also on the data that's available at runtime. So you have to use a library in your build file basically, and then you can add this feature where this works along with the macros thing. That takes care of the static part, and this takes care of the dynamic part. Now let's also understand, like from the functional programming perspective or from the functional style, what are some of the benefits or limits that this metaprogramming facilities that we have just talked about has added to Scala. So the very first is the same that we have also discussed previously in one of the advantages. All the boilerplate code now can be removed. You really don't have to maintain. At times what happens, I come in a situation where I have to maintain a lot of boilerplate code, and even if we try to avoid it or we try to refactor it, we're not able to do. So using by following some of these techniques that we just have discussed, we can eliminate those instances, and we can eliminate all the redundant and the boilerplate code. Then the performance of application definitely was improved, and I can also leverage the performance by using one of the basically techniques that we have discussed. I can use reflection, I can use macros, I can use tasty inspection, those things I can use. And if I'm using macros, so definitely my execution time gets improved a lot, and I can also have a lot of maintain the readability of my code. I can write clean code with macros. So and I can increase also the reusability and maintainability part. So all those things can be taken with the help of this. Now let's quickly go and take some examples just to understand it better. So for today, we are mostly try to focus on these three things. First is the inline thing, then is the macros, and then there's the reflection. We'll try to cover all three, but just in case we're not able to cover, we'll at least cover inline and macros. So let's first start with a simple, what to say, inline example. So I have told you that inline is introduced like a basically a modifier basically that ensures that the definitions will be inline at the point of its usage. So what is happening is like for the methods, their body will be inserted at the place wherever these are called. For example, wherever I'm calling this val logging, it will be inserted automatically. And what are the benefits it's giving? For expressions, they will be evaluated on compile time if I'm providing it like an expression. And if in case I'm using inline in some argument as a a parameter or as an argument, then they will be inserted at the place of its usage. So let's take this simple example of this config object. It basically contains the definition of inline value logging. that you can see, which by default I have set as of now to a constant value, that is Boolean, that is false. Uh, so this logging is treated as a constant, or you can consider as it a final value, just like we have in Java. It is something equivalent to the Java final variable that you can understand. So the right hand side of such an inline value must itself be a constant expression. That's one basically expectation. And now the logger object basically that contains the definition of your inline method log. This logger is basically containing my one method, that is this log. So we will see how I'm calling this out. So this method will always be inline wherever I'm calling it, wherever I'm using it. So let's simply take an example. So let's say I've called this object logger, okay, and I've called this method log. So if you can see the basically my what to say syntax of my method log. So I have passed some message which is of type string. Then I have passed a call by name basically parameter. By call by name parameter, I'm trying to invoke some kind of lazy evaluation technique. So I've passed a indent margin call by name parameter. So whenever it's used, then only it would be invoked. Otherwise, it won't be taking any kind of memory. And I have further basically given it an operation. Again, that's a call by name parameter which is of type T. So I am calling this logger and I'm passing some kind of string, and then I'm basically passing my first parameter, that was a string, some operation, and then I'm basically passing the second call by parameter. So as of now, you just for time being just say understand it has get converted internally into this indent setting. How it has got converted into this, we will just discuss in few minutes only. And then I am using a partial applied function on this. So I have just used a wildcard character. So that's how I'm trying to call this method over here. So let's take one simple example just to get more clarity. So let's assume that initially my value of this basically logging inline variable, or basically let's say it was equal to true. So if the value is true, then it will fall into this basically then basically a block, and when it was false, it will fall into this operation. So in case it is true, so basically what happens, the code actually gets internally written into this way. So what happened, it internally, let's say I'm doing some kind of, let's say, a factorial operation. So internally it will call my factorial operation. It will set all the values for the indent setting, that is the inline variable that I have, and then it will be internally calling like this. But let's say if my config.logging value was basically was set to false, that is it goes into the else block. So basically what will happen, this particular block will be taken, so that this particular pattern will be followed. So you can see this var indent setting thing basically is not getting used over in the else block. It simply calls my operation, which I have basically given over here in my call by name parameter. So what happens is, so since we saw neither the message nor the indent margin, they were used. They do not appear in the, the generated code for the factorial. And also we noted that the body of our log method, that is the else part basically, this part basically, just reduces to simple operation, whatever operation. Let's say we have given a factorial operation, so simply it will reduce to that particular operation. So in the generated code, we do not generate any kind of, closures, because we only refer to call by name parameter once. So the code was inline directly, and we can say that the call was beta reduced this way, the one which we have just seen over here. If you have to basically see in the terms of like how the compiler basically reduces this code, so actually internally it is getting converted into this. So when the logger.log method is basically getting called, so it is actually calling something like this. This is how it is being called in when it basically it converts it internally. We won't be able to see at the runtime, but at the background, it whenever the method is called logger.log, it internally gets converted into this way. Another point to note is that the call by value parameter message was evaluated only once, because as per the Scala semantics, by binding the value and reusing the message through the body of factorial, we have to do that way. And also we can also note that the special handling of the assignment variable. So we have if we have, let's say, some kind of private variable that I have declared over here, indent that we have over here. So what it happens, it is basically achieved by generating a some kind of setter method. So that setter method is basically this def indent inline dot in. This is the setter method for that private variable. So it is being called and it is set over there. So inline method always have to be, fully applied, and they can't be, partially applied. And also they can also, also have the capabilities of overriding other non-inline methods, but certain rules has to be followed. For example, let's say if you have to, if you have an inline method, simple say f, and it want to implement, or let's say it want to override some other non-inline method. So the inline method can be only be invoked at runtime. That's one rule. The second thing is that the inline invocation and the dynamically dispatched invocation, they always give the same result. And these inline methods have to be of, of the format like final. They have to be of some constant value. And also you can also make this inline methods abstract if you want, but the abstract inline methods can be, only be implemented by other inline methods, the usual abstract definition. That's so this way you can even override an inline method can even override other non-inline method, but by following all these what you say rules regulation it has to follow. Now let us also see a simple example of a macro. So first of all, for macros, what Scala 3 has done, it has followed two fundamental operations. So if you're not aware, I'll just quickly discuss about that. One is the quotation, another it is following is splicing. So quotation, basically what does it means? When an expression of this form, basically a hyphen then followed by curly braces, and if a expression is starting of this format, that is with a dollar symbol and then the curly braces, so that is basically splicing. Now what exactly is the difference between the two is, so what happens, quotation converts an expression, let's say of type T, to any typed abstract syntax tree. So high level expression could be something, this thing, expression of type, let's say unit. Also it converts the basically your type T to type T, a type representation that's used in your macros. So let's take a simple example this over here. For example, I have to print my all the constant values. So I'm basically trying to give the return type of this expression as of type unit. So this will simply basically print this particular value. So this expression will generate an expression of type unit of the function call. Let's also try to take an example from splicing. So let's say splicing, first of all, is in reverse of a quotation, or you can say opposite operation to your quotation. It evaluates first of all, and then embeds an abstract syntax into code. So let's take a simple example. Let's say I have to print all the uppercase implementation. That's what I want to do. So I've taken a string kind of expression. I'm using quotes, and my return type is again an expression which is of type unit. So for string, basically this str which I have, that is my variable which I've given as a what you say method argument, which is of type expression of string. The splicing of this dollar string, this thing, will evaluate to an AST, that is abstract syntax tree, and to convert it back to the code as to uppercase function needs to be called on it. Then I will be calling this basically uppercase function after it has got splice, and the generated expression, that is this one, is then embedded in my resulting code. So this was a simple basically example of splicing, where I'm basically converting a string expression or a string simply into an uppercase. If we want, let's also take a simple example. Let's say you have a simple string formatting, for what you say, syntax like this, simple string interpolation syntax like this. Now in this string interpolation syntax, what we did is I'm basically calling, if you can see, two dynamic variables. One is the user, and then I'm calling another dynamic basically variable, which is basically kind of expression, if you can see. So we quoted a string, and then what I did, we spliced it into it. So this is what we initially have quoted this string, and then we have spliced into it. So the first dynamic variable, that is the user, is a reference to the value of type string, and the second, that is my arithmetic expression, that will be evaluated followed by the splicing of its string representation. So quotes and splices, allow us to treat the code in a similar way, but they are part of the ways or operations through which I can effectively support my macros. Now let's take another example, basically the main method, the inline. So the entry point for any kind of macros would be your inline method with a top level spice, and we can call it a top level because it is the only place where we encounter some kind of splice outside the code. So this way you have to first of all declare a method, and you will be using this basically modifier inline with it. And then I have basically called a splice over here, splice expression over here. And if you can see, I'm using the, what you say, the argument for my, but this particular method is also again of type in basically inline. So this is the basically entry point for the macros. And in this example, the inline method assert, this basically is what it is doing. It calls at compile time a method which I'm using over here, the second method, that is the assert implementation with some kind of since this is a boolean kind of expression that I'm trying to use. So this boolean expression basically is used as an argument, and this assert implementation evaluates the expression, prints it again in an, if there is kind of error message or some kind of failure happens, and this only happens when it evaluates to false. So at that particular time, if not of expression, then I'm throwing some kind of exception or the basically failure message. Let's take few more things just to better understand how quotation and splicing works. So you can also use quotes and splices directly to your identifier. You can apply over them also. So let's say I have an identifier, like for example say $x. So whenever my identifier starts with dollar symbol, so basically that appears inside a quoted expression, or you can say some kind of type, then it is treated as a splice. This particular expression is of type splice. And if you it starts with an apostrophe, that is a code basically, then basically it is this quoted identifier basically will be treated as a splice. This was basically quotation, and this was the thing is treated as splice, but it has to be within the curly braces. That's what I'm trying to explain. Now there's one more thing. These codes or these quotations and splices, they are like, dual in nature. Like for any kind of, let's say, arbitrary expression, like I have taken over here. Let's say I have an arbitrary expression E. I'm saying I have applied a dollar symbol. Then I'm giving in basically curly braces. Then I'm further applying, splicing on it. That is apostrophe I have applied. So if I have applied quotation and then splicing on it, it will give back me the original expression, or the vice versa. If I apply the splicing then quotation, it will give back me the expression. So that is what is said, key codes and splices are like duals of each other. Let's take one more example. This is a simple, example which we can demonstrate any kind of abstract syntax tree. So what I did, since it's a macro, I created an inline definition. In this inline definition, I have given an expression which is of type T, and I'm returning back another method, that is the abstract syntax tree implementation, and I'm returning back the expression. I'm returning this as expression. So within this method definition, what I've given, first of all, I have to import this particular library, that is codes or reflect. So this basically library will be used when you have to use for the abstract syntax tree. So I have added some kind of what to say loggers over here, printlns over here. So first I've said, let's say this tree is of type dot show, the type which I have given over here. So it will simply show me, and then I'm saying I'm using a simply just to print all the terms of this abstract syntax tree. So I'm using that over here. So printer.tree NSI code or printer.tree structure will give you all the elements of your AST. So that's what it is doing. And then some printlns I've added just to add a new line. That's what I'm trying to do. And in the end, like this was the expectation, I'm returning back my expression. So let's say I've basically created an object for this particular log AST, and so when I will actually call this class instance. So what will happen? It will print the output in this format. So first it will print tree of type, since my class is A, so it will print that thing. Then it is basically printing. If you see the second println, the NSI code thing it will print, that is your new, and whatever is your class. So it was a class, so it will print the object construction, and then in this tree structure it will print all the elements. So in line followed by no elements, like I have given or initialized over here. So it will print like null, nil, those kind of things over here. And in the end, it is telling me that the new type indent is of type this class name. It will basically print over here, and then it will tell if it has any kind of initial elements. So those things it is printing. So these are the elements, and these are basically the tree type. So type dot show printer or tree and si code printer or tree structure. These are some of the methods that you can use, to see the elements or to print your AST. That's how you can do it. Okay, if time permits, then let's move to reflection. Else, what we can do for now, let's see the reflections like probably in the next basically session, because it will require some details and the implementation part for better understanding. But for now, if there is any queries with respect to macros or with respect to inline, so we can quickly discuss. Otherwise, I will move to the rest part of the slide. Okay, if not, so assuming this as a no, I will move on. So these basically snapshot are the same examples that I've shared. So I have tried sharing for all the features, like for inline I've shared, macros I have shared, and then I've also shared for the reflection that I have shared. Then I've shared an example of taste inspection also. I have shared how you can create. Maybe for timing you can refer to this example. In one of the subsequent sessions we'll also try to cover some more details on it, like how we can apply these things in our day-to-day use cases. You'll see that part. And then there's also example from compile time operations over here. In the end, like I can conclude by saying, like for any statically typed language, like Java or Scala, so metaprogramming, even though it's like restrained or like I can say constrained, but at the same time it's like very useful, for solving many real or advanced real-time design problems. So they can be solved easily, by following some of the metaprogramming techniques that we just saw in Scala 3. Similarly, it would be there in other languages also. And also it provides more flexibility and configurations during runtime. So that is another benefit that it provides. And overall what happens, the code readability, the expressiveness of your code basically will increase. And plus it will also provide a lot of flexibilities. But yeah, there's one more thing. We need to use metaprogramming very cautiously, because like I said initially, the learning curve is really steep if not used properly. So it can lead to a lot of havoc, and a lot of mess it can create. Because since metaprogramming gives you a lot of flexibility and configurability at runtime, so misuse or incorrect use of that can also result in unwarranted or any kind of unexpected errors that can be extremely difficult to debug. Because we discussed that debugging is something that's one of the limits of it. It doesn't have that mature tools to do it as of now. So it can introduce a lot of risk into the system if not used cautiously, and it can make your system more vulnerable if you haven't used it wisely or properly with care. So those are some of the common problems that can occur with wrong usage of metaprogramming, and also can make your compiler what to say incapable to identify any kind of missing configuration parameters or any kind of incorrect data or invalid data. And it can lead to what to say incorrect results and data at the end, and a lot of incorrect what to say exceptions and unknown exceptions could also be there, or what to say undesired results can come at the end. So yeah, we can use, it's a great technique, but it should be used carefully and with the proper knowledge. That's the only what to say suggestion that is there. Yeah, that's it from my side. If there is any queries or feedbacks, we can discuss. Thank you, everyone.